to actually save that in the class, and that's why I lost it here. But I will add them later on, and I will upload the solved version. This is where we stopped in the class, if I remember correct. Am I correct? I think I can close this. The viscosity of a fluid is to be measured by a viscometer constructed of two 75-centimeter long concentric cylinders. These are the cylinders. The outer diameter of the inner cylinder is 15 centimeters, that is this one, and the gap between the two cylinders is 1 millimeter. The inner cylinder is rotated at 300 RPM, and the torque is measured to be 0.8 Newton meter. Determine the viscosity of the liquid. We just straight need to go to the equation in this case. So if you go to the formula sheet, can you see? Remember, the formula sheet cannot describe the whole of fluid mechanics there. The equations are, you need to familiarize yourself. I'm not going to state, oh, this is Bernoulli equation in this form, this is Bernoulli equation. No, I just give the Bernoulli equation. And also I'll give you that equation, that is T equal to mu times and all of that. That is the relationship that is connecting the torque to mu, which is the coefficient of friction. So you need to pull out that equation, T equal to mu times 4 pi squared R cubed N dot L over L. This is the equation we use in a viscometer to calculate the viscosity, where mu is the viscosity. So take that and go to the problem that is given. This. So I'm just pulling out that equation and rewriting it for mu. So mu is equal to T times L divided by pi squared 4 times pi squared R squared N dot F R cube, whatever you say, sir. Once you said that, as I said, no one can question you. Yeah. This is the equation we just rewrote. There is nothing difficult here. Only thing is being familiar with these equations. The length is given as 75 centimeters, which is 0.75 meters. R is 15 centimeters divided by 2, because diameter is given as 15 centimeters. So R is equal to 7.5 centimeter, which is equal to 0.075 meters. The gap between the two cylinders is L, is equal to 1 millimeter, which is 0.001 meter, and the torque applied T is equal to 0.80 Newton meter. So all the units are consistent now. So the dynamic coefficient of friction mu is equal to torque 0.80 times L 0.001 divided by 4 times pi squared times R cubed, which is 0.075 0.75 cubed times revolutions per minute is 300. But in this equation, you should substitute it as revolutions per second. So that is divided by 60. RPM is converted into revolutions per second times what is the last quantity? L, the length, which is 0.75 meter. If you solve that, mu is equal to 0.01281. The unit is Newton second per meter square. Pardon? 0.075? Yeah, this is 0.075, but this is 0.75. That is the length, the full length of the cylinder. All right. So it's a simple problem. There is no complication. Just need to know what it is and where it is coming from. The next problem is very interesting. Can we move on? Can we? You can consider this as an important problem. A thin 30 centimeter by 30 centimeter flat plate is pulled. That is this plate. There is a plate like this. Its area is 30 centimeter by 30 centimeter. The thickness is negligible. It is pulled through the center of this fluid volume. And by applying a certain force F there. All right. And it is pulled at 3 meters per second. That is the velocity with which you are pulling it. 3 meters per second horizontally through a 3.6 millimeter thick oil layer. So this oil layer below the plate is 2.6 millimeter and above that is 1 millimeter. And somewhere there you are pulling it through. The dynamic viscosity of the oil is mu equal to 0.027 Pascal second. Newton second per meter square or Pascal second, both are same. The top plate is fixed and the bottom plate is moving with a velocity 0.3 meter per second to the left. All right. The dynamic viscosity of the oil is 0.027. We have written that. Assuming the velocity in each oil layer to vary linearly, plot the velocity profile and find the location where the oil velocity is 0 and determine the force that needs to be applied on the plate to maintain this motion. So let's see. Let me draw a slightly magnified version of this picture here. So we have the top plate, which is fixed. And there is the bottom plate, which is moving to the left with a velocity 0.3 meter per second. And we are using this central plate by applying a force on this, and this is moving with a velocity 3 meters per second. And this is fixed plate. For example, if I take any reference line here like this, the velocity profile in the top portion of that changes from 0 here to 3 meters per second in a linear fashion like that. That is the velocity profile there. Would you accept it? Because that plate is moving with 3 meters, so the fluid that is sticking to the top surface, it will have no slip condition there. It will move with the plate. So the plate is taking the fluids here, the fluid film there at that velocity, while that fluid there will be attached to the stagnant surface, 0 velocity. Similarly, the bottom plate is moving this fluid with 3 meters per second, 0.3 meter per second that way. And from there to this point, the velocity profile is going to be like that. Because he said that the velocity from one plate to the other plate is varying as a linear profile. And so where is the velocity becoming 0? This is where the velocity is 0 in between. All right. Now, if I call this point as A, where is it coming from? Where is it lying? And to identify that, let's say this is the height from the bottom where that velocity is becoming 0 in the fluid film, YA. And we know this distance is given as what? 2.6 millimeter. And that distance is 1 millimeter. All right. Now I want to establish YA. Can I say 2.6 from similar triangle principles? Two point six minus YA divided by YA is equal to 3 over do you accept this? Similar triangles, when two triangles are having any 3 dimensions equal, they become similar triangle. The ratio of corresponding sides is equal. So this side is 2.6 minus YA for that triangle. That divided by, for the lower triangle, YA, corresponding side, that ratio must be equal to, for the bigger triangle, that is 3, for the smaller triangle, that is 0.3. So the ratio 3 over 0.3 must be the same as the ratio of the other two. So I use that principle there. And from that, we can calculate, by simplifying this, we can calculate, therefore, equal to 2.6 and simplifying this, we can calculate what is YA, and that is equal to 0.2364 millimeters. So at a height of 0.2364 millimeter from the bottom plate, the velocity of the fluid layer will be 0. for this problem. All right. Then for the next part, he's asking you what is the total force that is applied on that plate. So for that, we need to look at this formula sheet. Can you see the shear stress that is applied by a fluid film on a surface is equal to viscosity times du over dy, where du over dy is the slope of the velocity profile. That is a relationship in a Newtonian fluid. So if you pull that equation out, that tau is the shear stress applied by the fluid on the surface on which it is in contact. And du over dy is the slope of the velocity profile. If you just bring that here, we can write for this plate, when it is moving, there is a shear stress applied by this plate on the film like this on the top side, and there is a shear stress applied on the bottom side. So let's call this as tau s upper surface, and this as tau s lower surface. Now the tau s, if that is the case, the force applied to achieve that shear stress is equal to force on the top surface is equal to the tau s on the upper surface times the area on the top side of the plate. But tau s upper side is not supper, remember, it's time for supper, but it is tau s upper surface. Okay, tau s is mu times du over dy. That is the slope of the velocity profile there, times the area of cross section. So this is the equation part, and you know force equal to stress times area of cross section, because stress is force divided by area. So this is the shear force applied by the plate on the fluid on the top. So this is equal to mu is given in the problem as 0.027 times the slope of the line in the top is nothing but that height divided by that length. So which is equal to no, actually the slope here is the velocity change du is the velocity change divided by dy, the vertical height. So this is the velocity change is from 0 to 3.0. So velocity change du is 3.0 divided by dy. It's happening in a vertical length of 1 millimeter. But that 1 millimeter we can't write in millimeters. So you need to convert that into meters, 0.001 to make it consistent with that, times the area of the plate. What are the dimensions of the plate given? That is a 30 centimeter by 30 centimeter plate. So the area is 0.3 times 0.3. That is the area of the plate. This is du over dy, change in velocity divided by the change in the vertical height. So from this, we can get the F acting on the top surface as equal to 7.29 newtons. In a similar way, F, what did we call this as? Lower. So F lower or bottom surface equal to tau lower times the area of the plate on the bottom surface, which is equal to mu times du over dy times area. So this is equal to mu is again 0.027. And what is du here? From 0.3 to minus 0, oh no, from 0. No, from 3 to minus 0.3. That's the reduction. So the slope will be the total change in the velocity from the top to bottom will be 3.0 minus of minus 0.30, which is total of 3.3 variation. All right, divided by the height is 2.6 millimeter, which is 0.0026 meters times the area of the plate is
What? I can't work on
0.3 times 0.3. All right. You understood why I put minus minus? Because it's the other way around. The total velocity is changes from 3 on this direction to minus 3 at the bottom. It means minus 0.3, which is 3.3 total variation from one plate to the other. So from this, F lower or below is equal to 3.08 Newton. Therefore, the total force is equal to the upper one plus the lower one equal to 10.37 . We're only using one equation from the formula sheet in this case, which is the shear stress applied by a fluid film on any surface is mu times du over dy. The rest of it is general knowledge. Okay. Anybody, this problem is an interesting problem, an important problem in my opinion. Online, any issues there? Daniel Pillai. Oscar McKenzie.
I'm good, sir.
Emerson Dewitt.
No questions, sir. Thank you.
Raghav Barla.
Sir.
Fahim Khan. You all. All right. What is the time? 4:45. We can solve one more problem at least. This one I'm not solving because this is again a question for the model exam. Half of it is the same as what we did in the statics course. Half the problem is the force required to move that block up that slope in dry condition when friction is applied. You need to draw the free body diagram and put all the forces parallel and perpendicular to the surface and use sigma Fy equal to 0 and sigma Fx equal to 0. We solve these problems in statics. That is one half. Then he adds, if there is a film of oil between the two of some thickness and some viscosity, how the force will be reducing. It's an interesting problem. That's where the frictional, the shear stress applied by this film, tau equal to mu du over dy, comes into picture. From that tau, we can calculate the resisting fluid friction instead of dry friction, now fluid friction, and then you will get a different frictional force there. And if you use that, you will get the F value lower or higher. It will be lower than the dry case because the oil film will actually reduce friction. Right, but this is the model exam question. I will solve this later on. Also consider this as an important problem. Okay. All right, there are some conceptual questions coming in here. Let's go through them and then see if you are fine with them. What is surface tension? What is its cause? Why is the surface tension also called surface energy? So we discuss all of this. The magnitude of the pulling force at the surface of a liquid per unit length is measured or defined as the surface tension force. The magnitude of the force at the surface of a liquid per unit length, Newton per meter. That is surface tension. It is caused by the attractive forces between molecules, cohesive forces. The molecules on the top surface have unbalanced cohesive forces, and so they will be getting pulled by the friends inside. But then there is a compressive resistance happening in the top layers, which makes unnecessary complications for the liquid. And nature always tries to avoid these complications. The easiest thing that you can do is to go to the lowest energy state. So it tries to reduce that surface area to a minimum. That is the driving force to get into the surface tension. It is also equal to the energy required to the surface required for the surface area required to maintain that surface per unit area. So this is also one of the definitions, and I've shown an equation in the handout where the energy that is associated with that surface is shown as also equal to the surface tension in the liquid. But generally, we treat it as Newton per meter. The force required per unit length of the surface is the surface tension. What is the capillary effect? What is its cause? How is it affected by the contact angle? We know the capillary effect is due to the differences in the adhesive and the cohesive forces acting on a liquid column. The cohesive forces are the forces within the molecules of the liquid which are trying to pull it down. But then the adhesive forces are due to the attraction to the molecules of the surface of the tube or the wall on which the fluid is trying to climb or fall down. The contact angle, if it is less than 90 degrees, then that adhesive forces with the wall will be higher than the cohesive forces within the liquid. And in a capillary tube, the liquid will rise, like water rising, because its contact angle is almost zero. But if the contact angle is more than 90 degrees, then the adhesive forces will be dominant, and that liquid will be pulled down in a capillary tube. Example, mercury, which has a contact angle of 137 degrees, and that will actually be lowered in a liquid in a capillary tube when you insert a fine tube into a pool of mercury. The liquid will be below the free surface level. If you put it in water, that liquid level in the capillary tube will be at a higher level than the free surface of water. These are the reasons. Consider a soap bubble. Is the pressure inside the bubble higher or lower than the pressure outside? Here it is higher inside than outside. That is why the film, the surface of the bubble is stretched. And to what extent you can stretch it depends on the surface tension force. If you cross that surface tension force that can be generated by that bubble, it will explode. Is the capillary rise greater in small or large diameter tubes? In smaller diameter tubes, the capillary rise is bigger because if you look at the equation for the capillary rise, where is it? Capillary rise H equal to 2 sigma S over rho G R cos phi. Phi is the contact angle. Sigma S is the surface tension force Newton per meter. So for a given liquid with different given conditions, phi and sigma S are known, and the variables are the radius. If the radius is, because it's in the denominator, the smaller the denominator, the bigger is the result. So H will be higher with smaller capillary tubes. Okay. Determine the gauge pressure inside a soap bubble of diameter 0.2 centimeter and 5 centimeter at 20 degrees Celsius. What is the time? We still have time. We can solve this. Let's solve this. So the first part, A, the diameter of the soap bubble is 0.2 centimeter. Immediately, I get tempted to change it to meters because I'm comfortable looking at meters. I can feel that things are under control. Okay. The temperature T is 20 degree Celsius. Let's not get too worried about the degree Celsius at this stage. We need to look at the equation which is using this, then we will. The surface tension this is actually telling you what is the surface tension of the soap bubble. This is not given in the problem, but that is data. It has to be given. Sigma S at that temperature is equal to 0.025 Newton per meter. All right. We don't need to remember these equations. We just go there. Delta P, that is the air droplet, and for a soap bubble, the thickness is considerable. So we use 2 pi r 2 times. This is the equation we should use. The pressure difference is equal to delta P equal to 4 sigma S over R. Just that. And bring it. So delta P is equal to P inside minus P outside, which is equal to 4 times sigma S over R. So substitute what we know, 4 times 0.025 divided by the radius is half the diameter, which is 0.001. Therefore, delta P bubble is equal to Can you calculate this and let me know what this is? Can you tell me what this is? I haven't done that. Yeah. All right. And when D equal to 5 centimeter, which is equal to 0.005 meter. The same thing. D over 2 is the radius. So from this, am I correct? 4 Newton per meter square. All right. All right. That's just the use of the equations there. Okay, continue. Still have 5 minutes. You can do a lot. Oh, my watch is running slow, man. We have 1 minute. A 1.6 millimeter diameter tube is inserted into an unknown liquid whose density is 960 kilogram per meter cube, and it is observed that the liquid rises 5 millimeter in the tube, making a contact angle of 15 degrees. Determine the surface tension of the liquid. So, what is surface tension? Go back to the formulae here. So, the surface tension of a liquid and the contact angle and all of that, that is the equation. Capillary rise H equal to 2 sigma S over rho G R cos phi. So substitute that data there. So we bring that equation. Let me just quickly do that. Rewriting that equation for sigma S is equal to rho G R H divided by 2 cos phi. You may be surprised at where this equation is coming from the formula sheet, okay? So substituting the known quantities, you get sigma S as equal to 0.0195 Newton per meter. I will leave this with you to solve at home. And I will continue solving these problems like this. I will see you on Thursday again in the class. We will complete them most probably by Thursday. And after completing this sheet, I will go to the fluid statics sheet and then solve and complete everything. And the next week is heat transfer. Online, any issues?
No issues.
So we
Thank
are
you, sir.
winding down. I'll see you all on Thursday. Thank you for joining.